Hi everyone, my name is Abhijit Suresh. I'm a PhD student at the University of Colorado Boulder. Today I'll be presenting my paper on using transformers to provide teachers with personalized feedback on their classroom discourse, the TalkMoves application. So the primary goal of this research is to address a significant challenge in mathematics instruction, which is providing teachers with immediate and actionable feedback on their effective use of classroom discourse. At present, providing teachers with feedback on classroom discourse needs the presence of an instructional coach or an expert. The goal of this research is to automate this process using machine learning and natural language processing. For this study, we are focusing only on mathematics instruction from grades 3 to grade 12. So talking about classroom discourse, we draw from one popular framework called Accountable Talk Framework. So these classroom discourses are well established in education literature to support teachers to provide rich classroom environments. So it's broadly classified into accountability to the learning community, ensuring purposeful, coherent, and productive group discussion, and accountability to rigorous thinking, which can be further divided into individual classroom discourses, also known as talk moves, such as pressing for accuracy. So, for example, if the teacher says, "Can you tell us the steps you used to find the answer?" That is an example of pressing for accuracy. So, the goal of this research is to create a deep learning model or develop a system that can provide feedback to teachers on these different types of classroom discourses. So let's start with an example usage scenario. So it starts with the teacher collecting classroom recordings through using technologies such as Swivel. So for folks who does not know what Swivel is an hardware device through which we can collect video and audio of the classroom recording when it's during session. So this video and audio is then taken by the TalkMove system to identify different types of instructional discourse by passing it through a big data infrastructure. And once we generate all these different measures, the TalkMax system then provides teachers with the different types of feedback through a web application interface, like a user interface. So one example of such feedback would be the ratio of teacher to student utterances, which is nothing but the number of sentences spoken by the teacher and number of sentences spoken by the student for an individual classroom episode. So using this feedback, we help teachers modify their classroom instructions to include more talk moves in their future classroom sessions. So to talk about the educational motivation of this research, it is well known in mathematics instruction education literature that students learn best by engaging in rich classroom discussions. But this requires teachers to change their instructions and focus on creating such environment. So although there are different research-based frameworks to do that, we pick one popular framework called Accountable Talk in order to develop deep learning models that are capable of recognizing these different discourse moves in from the classroom recordings. So looking at the classroom episode, this is an example of an annotated transcript. So this transcript has like the different teacher and the student utterances, and also the corresponding classroom discourses associated with it. So for example, if the teacher says, "But let's take a look at the ounces of coffee task. Any of you coffee drinkers?" So this is a good example of the talk move keeping everyone together. So similarly, we have two different human annotators annotate like a lot of transcripts, which served as the training data for the deep learning models. So to give you an overview of this application overview of the TalkMoves application, we have the web application through which the teachers upload and submit the different recordings, which goes into the big data infrastructure. So the big data infrastructure is implemented using Amazon Web Services, and the role of big data infrastructure is to prepare the classroom recordings, transcribe and segment the audio, and using the deep learning models, label each individual talk moves. Once the individual talk moves are labeled, then we can generate different feedback and visualization based on all these different pre-processing, and then like send this feedback to the web application to be shown on the website. So this is kind of a system overview of the TalkMoves application. So the data that is used to train the deep learning model was collected from two different sources. So the first source of the data was data collected from internet, from multiple sources, which such as a teaching institute channel. We had around 460 transcripts from that data source. The second data source is the data that collected from the TalkMoves application. We had recently deployed the TalkMoves applications for 2 school districts in United States, and we have collected around 300 classroom episodes from the TalkMoves application so far. It's an ongoing process, and as we speak, we are collecting more. So for training the data, we have transcripts of entire lessons and short excerpts from these lessons. So the number of sentences is approximately around 200,000, which includes both teacher and student sentences. And we have a detailed annotation protocol. We have 2 human annotation experts who annotate each individual sentence with a high inter-rater agreement, more than 90% for all the 6 different TalkMoves. So before getting into the model, I just want to give you a quick overview of the transformer architecture. So transformer architecture was a recent development in natural language processing that has shown remarkable improvement in performance in different downstream tasks. So the idea of transformers originally originated from this encoder decoder model, like a machine translation model, where the input to the model would be a sentence in, say, English, for example, and the output would be in French. So what researchers found was, if you just take the encoder block and stack them, you can train a deep learning model to produce contextual sentence embeddings. So this led to transformers, and the one popular transformer is the BERT architecture. So the BERT model is trained using 2 different steps. And the first step is the pre-training phase. The second step is the fine-tuning stage. In the pre-training step, they use something called a masked language model, where they mask individual tokens from the sentence and train the model to predict the masked token. And using this, they found that the model is able to better represent the really does a good job in to represent the embeddings for like a group, like each individual token with respect to that sentence. So once the pre-training phase is complete, so with this contextual embeddings, they use this contextual embedding vectors to fine-tune for multiple tasks, such as downstream tasks such as named entity recognition and sequence classification. And results have shown that this transformer architecture has performed much better than previous architectures such as bidirectional long short-term memory networks. So for the TalkMoves application, we leverage this new architecture. So the input to the model is the student teacher sentence pair, and the output is the probability distribution of over the 6 different TalkMoves, and the none, which is basically that it does not fall under the 6 different TalkMoves. An example of student teacher sentence pair would be the teacher saying, okay, why do you think they hate the growth spurt earlier, with the previous student context, which is, I said they hate the growth spurt earlier. So this in the figure below, you can see that the previous student sentence and the teacher sentence tokens are organized into one single vector with 2 specific tokens. One is the separated tokens referred by SEP, which separates the 2 different sentences. And the first is the CLS, which also represents classification. So basically, you're telling the transform architecture that this is a sequence classification problem. So this is the input and the output that we provide to the model for the TalkMoves classification model. So we have tried out different variants of BERT, transformers architecture. And so in transformer architecture, there are 2 different models, which is the base and the large models. The difference between base and large model is nothing but the number of encoder blocks and the number of parameters involved in it. So large models are usually has a lot of parameters when compared to the base models. So in this slide, I want you to focus on the best performing models, which is the Roberta base for the under the base models, and the Roberta large under large models. We calculate the performance on the test set using two different scores. One is uh, the micro FN scores, and the second is the Matthew correlation coefficient, which is a indicator, which is a value between -1 to 1. The more close to 1, it means that it is more robust to different testing sets. So now that we have these, we have integrated the best performing model into the application to do this job of like classifying the teacher classroom sentences into the different discourses. So to study the model, how the model functions and where we can improve, we generated a confusion matrix. So in this, you can see that you have the performance of all the different TalkMoves for Roberta Large, which is the best performing model, and this is the results from the test set. So two different like TalkMoves that performed low was revoicing and getting students to relate. So what we realized was one of the reasons why revoicing was not working as expected was because that the number of revoicing instances in the training sentences were low. So this is one of the issues that we had identified, and by collecting more data, we hope to resolve that. The second TalkMove that I wanted to focus on is getting students to relate to each other's ideas. So this performed low, also performed low, but I think the reason for this was because since we provide the teacher sentence with just the previous student's sentence, the teacher's sentence, the model does not have enough context information to associate students across the transcript or across the classroom session. So in the future, we hope to resolve this by increasing the context window to the entire transcripts rather than just student teacher sentence pairs. Moving on to the feedback, this is an example feedback what teachers looks after the classroom recording. So you have the classroom video, you have the different frequency of teacher TalkMoves, you have the teacher and the student talk distribution, you have the percent of TalkMoves by category, by quarter. We also provide information on the words that has been commonly used during the classroom session. And also we, in terms of class engagement, we provide information about how many number of students and how many number of student responses were student responses that had only a single word. For example, if the student says okay or yes, so those are examples of student sentences with only single word. We also provide feedback to teachers with more than 3 seconds wait time. So this is a good practice to wait for a sentence before delivering it. So these are the different types of feedback that we currently provide. We are still focusing to improve this to provide more different types of feedback, such as the trends across different classrooms for individual teachers. So to talk about limitations, the challenges, limitations, and the next steps. So due to the COVID-19 pandemic, we had some difficulties with the data collection process since all the classrooms went online. However, we resolved that recently by upgrading the big data infrastructure to support uploading Zoom recordings and other types of recordings. Uh, and one other major challenges was speech to text conversion. The current audio to text transcript conversion, we use Amazon Transcribe services. While the Amazon Transcribe services is really good for, say, adult speech, it still has a lot of difficulties recognizing kids' speech. So as part of the next step, we want to improve or create new models to improve the performance on speech to text conversion. We also want to brainstorm if there are any patterns, underlying patterns in the student addresses, and to say that can we identify, like say, student TalkMoves in the literature and create supporting model to recognize the different student talk moves. And one thing that we are doing ongoing process is to get feedback from teachers through surveys and interviews on the usability of the interface, and then making changes to the user interface to make it better. And finally, we would like to next step for the deep learning model is to train the deep learning models with larger context windows to capture uh, long dependencies like transcript level dependencies. For example, getting students to relate each other to improve performance on such talk moves. So we are the TalkMoves team, and this project was funded by National Science Foundation. And yeah, so thank you for the opportunity and looking forward to the questions.